the most elegant math problem I know doesn't use any numbers. I was initially introduced to this puzzle at a math summer program, and this puzzle stuck to me as something seemingly proposed as a riddle for kids, but really has an elegant and intuitive solution relating to powerful, deep, and interesting topics in mathematics. As mentioned earlier, this puzzle doesn't use any numbers. This is important to me because throughout high school, I noticed that math is portrayed to the general public merely as a tool for assisting with better understanding physics and chemistry. And all that there is just plugging and solving equations, and I wanted to change that perspective. Many areas of mathematics are pursued simply for its elegance rather than any necessary applications, although many of which do eventually end up having applications. Without further ado, let's move on to the puzzle. Suppose you have two stakes in the ground and you're trying to leash Marty Lou with. Of course, let's assume that the two stakes are very tall, so tall that Marty can't just pick up the leash and unleash himself. Let's also assume that the leash is infinitely strong and infinitely stretchy. Further, from time to time, the farmer wants to unleash him to let him go out for a run, but the farmer is very lazy. Instead of undoing the leash, he simply wants to pull the stakes out. But the farmer is even lazier than that. He only wants to pull out one stake to unleash Marty, but he still wants to ensure that if neither stakes are pulled, Marty still can't run away. Let's do an example. Perhaps the most obvious way to start is by leashing him to both stakes in the following manner. Of course, Marty still can't get away, but pulling neither stake wouldn't release him. Next, let's try only looping around the top loop. Of course, Marty once again can't get away, and pulling the top loop actually allows him to be released, but pulling the bottom does not. We want to have it so that pulling either stakes would release him. Lastly, let's try a more complicated example. Again, Marty can't escape, and pulling the top stake does release him, but pulling the bottom does not. So in summary, firstly, there are two stakes. Secondly, Marty is leashed when no stakes are pulled out. And thirdly, Marty can be unleashed when one stake is pulled out. I'll give you a moment to try this on your own, but I urge you to watch the rest of the video regardless of if you have solved it, since I'll explain not just the solution, but the entire process of how to approach the solution, the motivation along the way, as well as its ties to deep mathematical roots. I'll also give you a quick hint. Suppose you have found the answer. How would you describe your answer to someone without drawing it out for them? For most puzzles, the first step is to simply abstractify. But what does that mean? Generally, a good first step is to remove unnecessary elements. For example, the Bridges of Königsberg is a puzzle asking how to visit every bridge in Königsberg without visiting any bridge twice. The first step in abstractifying here is to label the mainlands with dots and replacing the bridges with lines, since that is the only information we need. Likewise, we can reduce the Marty Lou puzzle by removing the farmer, reducing the elements of the diagram to just the field, which we can interpret as a plane, two stakes, which we can represent as two circles, Marty himself, which we can just represent as a point, and of course the leash, which we can represent as a curve. You may have already noticed that we have already done a layer of simplification by reducing the situation from 3 dimensions to 2, as this is merely a bird's eye view. Also, note that since the curve has to start and end at the same point, namely at Marty, the leash is also a loop. One last constraint is that the leash cannot go through the stakes. We can actually interpret this as the plane having holes instead, which the loops cannot go through since the loops are completely contained in the plane. To better picture this, you can imagine the field as a piece of infinitely large paper with 2 holes in it, and any loop as any line not necessarily straight you can draw on the paper without lifting your pencil, which actually helps demonstrate another property. The loop, like all curves, has to be continuous. A simple question to begin with is this: how do we know if 2 loops are the same? So what I mean by same in this context is that the 2 loops function identically. That is, under the same conditions, either no stakes pulled, 1 stake pulled, or 2 stakes pulled, Marty can run away from either both or neither. A simple start is this: if you can move one loop to the position of another, allowing stretching or bending the loop, but not allowing passing through the holes, then they are equivalent. More specifically, they have to make a movement completely within the plane, without passing through the stakes. Now what happens if we pull a stake out in the original scenario? This is actually equivalent to filling the hole in the plane, since now the loop can pass through the hole without any constraints, just like how it can pass through the stake without any constraints. Thus, with this new layer of abstraction, the question simplifies to how to construct a loop such that it is equivalent to a loop passing through neither holes only when we fill one of the holes. That is, there's no way to move the loop to the loop passing through no holes unless we fill one of the holes. So in summary, we simplified this puzzle down to a 2D plane with two stakes, or a plane with two holes, and Marty as a point, and the leash as a loop confined within the plane. And also the leash must follow the following constraints. It is within the plane completely, and two loops are equivalent if they can move through each other through a motion completely confined within the plane. It may actually seem at this moment that this layer of abstraction only complicates the question further. But using these definitions, there's actually a way we can rephrase the puzzle into another simpler puzzle that is significantly easier to solve. To rephrase it, the first step is to go back to the hint of how do you describe a loop to someone without drawing it out? There's actually a very interesting observation that could significantly help us out here. Some curves are very simple, such as the loop not going through any circles. Let's call this the unloop since we'll be referring to this a lot later. Some are more complicated, such as this one over here. However, notice that we can break this into two parts. The counterclockwise loop around both circles, then the clockwise loop around the top circle, which is actually equivalent as shown here. We can write this as follows. The more complicated orange loop is the same as the blue loop followed by the green loop. But wait, we can actually go further. We can split the blue loop around both circles into two loops, a clockwise loop around the bottom and a clockwise loop around the top. Then just like regular arithmetic, we can substitute the second equivalent relation to the first. So we can describe the first loop in terms of three significantly simpler loops, clockwise around the bottom, clockwise around the top, and clockwise around the top again. But now you may be wondering, can we do this for all loops? Can we break down all loops into simple loops? And if possible, what are the simple loops? Which loops solve the original puzzle? This is important for us because, if possible, we can describe every loop as a sequence of simpler loops instead of drawing it out for someone, which was the motivating question earlier. It may be possible to see this immediately, but I will make this a bit more clear by another observation. At the moment, it feels like there are a lot of possible loops, but because most loops are equivalent anyways, we can change the setup a bit. Firstly, notice that it doesn't actually matter where we put the holes and Marty. The results will be the same. It doesn't even matter if the holes are circular, that's just done for simplicity. So let's move the holes closer together and make them a bit bigger and move Marty to the middle of the two holes. Secondly, by definition, there's no limit to how far we can draw the loops. We can actually draw the curve as far as we want, although of course this additional point of freedom actually complicates the question further. So let's limit that. Thus, to further simplify the possible number of loops, we can have a limit to how far we can move the loop away from Marty. In other words, we can add a boundary forbidding the curve to go too far. A quick observation is that it also doesn't really matter where the boundaries are. So of course, to limit where the curves can go as much as possible, we can move the boundary as close as possible to Marty and the two holes. So close that the only place the loop can go is along the edge of the two circles, which forms a figure 8. For example, the curve earlier would be equivalent to the following. Unfortunately, this is actually a bit difficult for us to see where the curves are going since there is actually overlap. I will relax the boundaries a bit for now. Let's return to the question of how to break down all loops. Firstly, you may notice that with this setup, it is indeed possible to break down every loop into a sequence of possible loops. This is because more complicated loops will probably pass through the center a number of times, so we can simply split the loops into multiple loops every time it passes through the center. For example, this is once again true for the loop we had earlier. Thus, to find all loops that make up everything, we can simply consider the set of loops that never passes through the center except for at the beginning and end. I'll give you a moment to find them. So apart from the end loop or any equivalent loops, there are only 4 possible loops you can make before ending back at the beginning where Marty is at. Namely, counterclockwise around the top hole, clockwise around the top hole, counterclockwise around the bottom hole, and clockwise around the bottom hole. And to see why this is true, let's first visualize loops on the figure 8 by imagining this as a bug crawling along the edge of the figure 8, and the loop being traced out by the bug. Notice that firstly there's only 4 directions the bug could go when leaving Marty: left up, left down, and right down. Now suppose the loop starts left up, then there's only 2 possible directions the bug could go. The bug could return to Marty, or the bug could make a full loop. The first of which is equivalent to an unloop, and the latter is equivalent to a clockwise loop around the top hole. Great, now we have a simple method to describe every loop. Although these are very nice, it's actually extremely bulky describing the movement since, as you may have heard, every single movement involves a direction and a hole. But fortunately, simplifying the notation is actually very easy. Let's get some inspiration from a slightly different topic. If you've ever learned to solve a Rubik's Cube, you may know that there are a lot of possible moves, and usually the Rubik's Cube algorithm or sequence of moves are simplified by a notation based on a sequence of letters, such as R', F, R, F', also known as the sledgehammer, which means turn the right face counterclockwise, front face clockwise, right face clockwise, and front face counterclockwise. We can actually use a similar approach to simplify these loops. Let's call a clockwise loop around the bottom hole B for bottom, a clockwise loop around the top hole T, a counterclockwise loop around the bottom hole B bar, and a counterclockwise loop around the top hole T bar. Thus, the example earlier is simply B, T, T. You might notice a few properties already. Firstly, for any loop, they are still a valid loop simply by moving the holes back apart and Marty back to the right. Secondly, you can interpret the sequence of moves as a list of instructions. So for example, the sequence B, T, T, if you do it in order and if you do T, T, then prepend it with a B, you get the same result. However, the order does matter, since it is easy to see that T, B, and B, T clearly look very different. In other words, how you put the sequence together doesn't matter, but the order you put them in does matter. Lastly, and most importantly, you may notice that if you do a B, then a B bar, they actually cancel out to simply an unloop, which we will call U. The same is true for T, T bar, and actually in this case the order doesn't matter, as the same is true for B bar B and T bar T. Further, if you have a sequence of moves containing T and T bar, only when they are right next to each other, they likewise cancel out. For example, B, T, T bar is equivalent to simply B, since the loop just undoes itself. In other words, we can actually randomly add B, B bar, T, T bar, B bar T, or T bar T, and the original sequence would be the same as the final. We can add this to U, for example. This is actually further evidence that order does indeed matter. If we consider B, T, T bar from earlier and T, B, T bar, the former simplifies to B while the latter does not. This can also be seen visually. Now, going back to the question, what do we mean when we fill the holes in? It's actually fairly easy to see that for a sequence, say T, B, T bar, removing the top hole simply is equivalent to removing all occurrences of T and T bar from the sequence, leaving only B. Thus, in summary, our puzzle is rephrased as follows. What is a sequence composed of B, B bar, T, and T bar not equivalent to U, such that removing all occurrences of B and B bar, or T and T bar, will result in the remaining terms cancelling out to form U? I'll give you a moment to try this out from here. One last critical observation is that removing certain elements could allow the entire thing to collapse to just U. For example, going back to the T, B, T bar, if we fill the bottom hole, Marty gets released, because the T and T bar cancel out. But if we fill the top hole, Marty does not. We're actually really close to the final answer. Since we want the sequence to cancel out when the top hole is also released, we want something to cancel out the B. So we can simply add a B bar at the end, yielding the final answer. Another way to reach this solution is to remember that the order does matter. So if we start with T, T bar, B, B bar, this actually satisfies our result, but it is equivalent to U, so that won't work for us. However, if we swap the middle T bar and B, so locking the sequence from collapsing to U immediately, we get T, B, T bar, B bar. Translating this back into the original diagram, this looks like the following. Clockwise around the bottom hole, clockwise around the top hole, counterclockwise around the bottom hole, and counterclockwise around the top hole. Here's to show that this does indeed have the properties we want. Pulling either stakes releases Marty. Of course, one question you may have is why we went through so much effort, since there are definitely simpler solutions out there. Maybe just from playing around with the puzzle visually. I initially found the solution without going through the trouble of moving Marty to the middle and all, but I found that the diagram with the figure 8 is so much more intuitive to show that there are indeed only 4 elementary loops that can build up any loop. Further, this approach makes generalizations of this puzzle significantly more approachable. The first simple generalization is to add another stake and ask the same question of whether we can release Marty by pulling a single stake. I won't go into the details, but essentially you can once again use the same definitions, moving Marty to the middle, moving circles to form a 3-component version of the figure 8, often called a rose, and giving yourself an extra letter, say R for right. Furthermore, you can also ask what happens if we want it so that only pulling 2 stakes releases Marty, but pulling 1 does not. And of course, we can generalize the problem to n stakes. You can also generalize so that when k stakes are pulled, it will release Marty, but when pulling any fewer, Marty does not get released. There are even more convoluted puzzles like coloring the stakes and only pulling all stakes of a single color will release Marty. These puzzles are actually called picture hanging problems, since usually it's framed as hanging a picture on 2 nails and pulling either nail will make the picture fall. These puzzles actually indeed do have solutions, and all build on the foundations I showed earlier, of translating the problem to a sequence of letters. In fact, there's a whole paper dedicated to these puzzles, all the way to a very generalized version of this puzzle which I didn't even completely comprehend, regarding pulling out subsets of stakes that would release Marty. You may also be wondering where some of the ideas in this video came from and may be interested in learning more. I decided to add this since I noticed that many of the other videos on this puzzle introduce very interesting topics but don't actually address where to learn more for viewers eager to dig deeper. Several of these ideas actually came from algebraic topology, and although algebraic topology is the topic generally introduced at a graduate pure math level, the definitions are actually fairly simple and intuitive, so I strongly urge you to take a look if you are interested and have some basic understanding of the definition of a group and the formal definition of a function. Firstly, homotopies are simply the equivalencies described earlier by continuous motion. That is, 2 loops are homotopic if there is a continuous motion between them confined within the plane. Secondly, fundamental groups are simply the group of loops such that 2 loops are considered equivalent if they are homotopic within some space and where you are allowed to combine loops via concatenation, that is, performing one loop followed by another. For example, in this video, the loops we dealt with form the fundamental groups of a plane with 2 holes and the fundamental group of a figure 8. Free groups are the groups of sequences of letters with inverses and where you're allowed to concatenate them like words. For example, the sequences composed of T, B, T bar, and B bar are equivalent, or in group theoretic terms, isomorphic to the free group of rank 2, which means a free group with 2 types of letters. Lastly, knot theory is a study of mathematical knots, which are essentially the same knots you tie your shoelaces with, but with some additional constraints and mathematical formalities. Many of the definitions in knot theory are simply fundamental groups in higher dimensions. Again, mathematics can come in many shapes or forms, at times as complex equations and formulas you have to memorize for your next physics quiz, but just as often as simple, intuitive, and fun puzzles designed for grade school children, which, as mentioned earlier, is formally studied and uses tools from algebraic topology. I hope this puzzle has shown you the more elegant and playful side of mathematics. I'd also like to thank the manimce community, as a lot of these animations would not be possible without them, and Grant Satterson, his YouTube channel is known as 3Blue1Brown, for hosting the Summer Mathematical Exposition Challenge, since it gave me the extra nudge to share this puzzle I've always been dying to share.